In this video, we're going to take a look at how integrals and derivatives are related. First, rather than just jump right into it, I want to kind of touch back on some ideas that we may not have seen in a while. And that is the idea of the inverse. And so here's just an example of just kind of a quickie. Suppose we had a function that took us from our home to the supermarket. Most of us would like to get back home at some point, and so we have a need. We need to undo going to the supermarket. In algebra, we learned that we can undo a function with something called the inverse function. And now for many of you, if you're viewing this video and you don't recall what an inverse function is, there are several videos out there that can instruct you on how to do it. Here's a quick down and dirty way of looking at it. If I have a function, we'll say y is equal to 4x plus 3. And this tells us how to do something. So I want to find a way to undo it. Well, first we need something called, we need to check for something called one-to-one. A function is one-to-one if for every input there is exactly one output, and if for every output there's exactly one input. In other words, we can't have an x that doesn't go to a y, and we can't have a y that doesn't have only one x value as its possibility. I chose a line here because it is one-to-one. However, all even powered functions for polynomials are not one-to-one necessarily. So you got to be kind of careful on this if you don't recall, and go back and take a look at what it means to be one-to-one in the horizontal line test. Anyway, we can go ahead and exchange the x and the y as a way to find this supposed inverse function. And so if we just interchange x and y, then this poses a reflection across the y equals x line. And therefore, if we solve for y, we can subtract 3 and divide by 4. That gives us y. And now we have something that is called the inverse function. So if f of x were to be 4x plus 3, its inverse function would be x minus 3 over 4. That would undo it. It would get us back to where we're going. Now, up to this point in your calculus careers, you've been dealing with something called the derivative, which looks at how the slope of a function behaves. Now, the slope or the behavior of a slope of a function can and often is its own function. And so, for example, you would take something as simple as f of x is equal to the sine of x, and its slope, the derivative of sine of x, is the cosine of x. That means for any value of x, the slope of sine behaves as cosine. Now suppose we knew how the slope behaved. We knew how the thing changed. Can we then find out what the original function was? And we have this need to undo something, but it's not a function necessarily. It's an operation in a very real sense. And so, rather than we have a function describing something, we have a pseudo operation that is changing the way the function behaves or the function looks. It is causing something fundamental to happen to the function. And so we're not just looking at a rule, we're looking at how it behaves. With that, my question is, if you were given the way it behaves, could you come back to the original function? That's what the antiderivative does. If the derivative looks at how a function changes, the antiderivative looks at the change of the function and then gives us back the original function. So we are looking at something called the integral. And the integral, in a very real sense, is the antiderivative. There's a little bit more to it than that, but in the simplest form, I guess you could call it, it is the antiderivative. So if I have the derivative of something, can you find the original function? Okay. So let's take the first example here. The derivative of a function is 3. The slope of the function is 3, no matter where you look. And so we have a constant derivative. Well, the only thing that makes a constant derivative is a line. So that we know it's going to come up with a line. Well, a line usually looks like mx plus b. But if we take the derivative of a line, its slope is m, and therefore our line should look like this. Now this brings up a nice interesting point here as well, because you have 3x plus b, but what is b? And b is this mysterious value that we don't know, and the question is, do we need to know it, really? If we take the derivative of 3x plus b, b is just a constant, the derivative of a constant is 0. And so we can take the derivative of a whole class of linear functions whose slope is 3, whose y-intercept is anything we want it to be. When we take the derivative, we get 3. So no longer is the integral guaranteed to be unique. Now we can have the integral describing a class of functions. In this case, it's the class where the function is a line with a slope of 3. After that, we don't care where it is. It's just a slope of 3. It can be shifted right, left, up, down, doesn't matter. Okay, let's take a look at another one. We have the derivative of a function being 0. Well, a function that has a 0 derivative is simply a constant function. And I guess my question is does it really matter what the value of the constant is? Not really. And so we'll just call it c for constant. And so if we take the derivative of any number c, we're just going to get back 0. That's it. The end. The most difficult of these three, though, the derivative of something is 2x. Well, we have an x in the derivative, which means we have to have probably at least x squared, or if not cubed, or to the fourth, or something like that, because when we take the derivative, we drop the power on the x by 1. Well, if it dropped by 1 to 1, its power must have been 2 at some point. So it must have looked like x squared. So if we take the derivative of x squared, oh, 2x, okay, we just happen to get lucky. Again, just as in the other two, does it matter what comes after it? Well, no, not really if it's constant. That's kind of the key here. We have to have a constant. So let's just go ahead and add on the constant. It doesn't matter what the number is, because when we take its derivative, it equals 0. This is the idea of the integral as the antiderivative. The integral is going to take us from the derivative to the original function each time we're adding on this constant value, because it doesn't matter what that constant is. We just have to call it something. So how do we write this? Let's suppose that I have some kind of a derivative function, and I wanted to find the antiderivative of it. And so when I did this, I'm going to start calling this capital F. Reason being is the capital F is the integral, and the little f is the, and we'll take care of this prime. The little f is going to be the function, or the derivative of the integral. So now, if I wanted to find this, first of all, I have to look at what is the antiderivative of f of x. But again, just like we took the derivative, we had to take the derivative with respect to something. Usually it was with respect to the variable that we used in the function. Here, it's again with respect to the variable that we use with the function. And so since our function variable is x, we take the integral with respect to x. Okay, and when we do that, we get our original function back. So as you can see, it's the integral is nothing more at this point than the antiderivative. Now, if we did that, we always have to add a constant on. And the reason being is when you take the derivative of a constant, you get 0. And so your original function can experience a vertical shift in either direction by any amount. And it doesn't change how the slope behaves. It simply changes how the original function looks.